Exercise 1, question number 1. We want to write the negation. All multiples of 3 are even. There are 3 options. And the option B, at least one multiple of 3 is odd. So this is the negation of this one. This is the statement. At least one multiple of 3 is odd. Usually, if there is a word all, so we have to use at least, usually, not always. At least. The common mistake can happen, all multiple of 3 are not even. That's how usually initially feel to do anybody. Not all, some of. But it has to be corrected as at least one multiple of 3 is odd. Question number 2. There are set of questions. We have to write the negation. All rich people are happy. So at least one rich people not happy. So this is the negation of that statement. The other one, there are no prime numbers between 10 million and 11 million. So now what is the reasonable negation? That is, if somebody is telling that there is no prime numbers, if we show, okay, there is a one number, that's enough. It means the negation is there is at least one prime number between, there is at least one prime number between 10 million and 11 million. And part C, P and Q are prime numbers, then PQ plus 1 is a prime number. If P and Q are prime numbers, then there exists a number that is not prime of form. So that's it, the negation. A number that is not prime. So from the statement it says PQ are prime numbers, then PQ plus 1 is a prime number. It means it is always. So if we have at least one, that's enough. So part D, all numbers of the form 2n are either prime number or multiple of 3. There is a number that is either not prime or not a multiple of 3 of the form to the power n minus 1. So this is the negation. Last one is at least one of the above statement is true. So none of the above statement is true. The negation is going to be at least. So we should not give any chance for them, none. Question number 3. If n square is odd, then n is odd. If statement, if n square is odd, then n is odd. We wrote the negation in the previous example. The same way, negation, we can write there is a number n such that there is a number n such that n square is odd but n is even. Um, Actually, there are few rules of writing negations. For example, if you use that for all x in x qx, then the negation will be there is x in x that not qx, something like that, and then assume for every x in x, then it will start there is an x in x, something like that. Like there are few rules. If I try to discuss those rules, you may get confused. So we'll stay with this knowledge and we'll move forward. We will start with n. So we'll consider n is even. So we can write n equal to m. Then we'll look at what is n square. So n square is 2m square, which is 4m square, which is 2 times 2m square. So hence n square is even. So n is even, so n equal to m. Then we found out what is n square. N square 2 times 2m square, which is hence n square is even. But n is even, n square is odd. That's the assumption. So instead of negation, I will write assumption. So assumption. So that is contradict, because if in this calculation n is even, we will get n square is even. But this statement say n is even, n square is odd. So this is contradict the assumption. So hence this is contradict assumption that n square is odd. Therefore, if n square is odd, then n is odd. Question number 4. We have to prove that there is no greatest even number statement. There is no greatest even number. This is true actually. Yes, there is no greatest even number. When you take the number line 2, 4, 8, likewise there is no greatest one. If you tell a number, I will tell the next one. If you tell me that number 10 is the greatest, I will know. I will tell at 2 and I will tell 12 is the next one. If you tell 998 is the highest greatest even number, I will add another 2 and I will take no, 1000 is the one. So likewise, when you will tell, I will add 2 and I will tell. So this is ongoing. So there is no greatest number, which is true. Now we want to write the negation or the assumption. So assumption is going to be there is a greatest even number. We'll consider a even number or even integer. Let's take there is a greatest even integer. Let's take 2 and we know that whatever n can be odd or even. When you multiply by 2 it is even. Now we are adding 2 to this one, but 2n plus 2 also an integer, and 2n plus 2 greater than 2n, that is also true, and 2n plus 2n is even, and plus 2 also even. So we know that even plus even is even. Hence we found out another even number 2n plus 2. Hence there exists an even integer 2n plus 2 greater than 2n. So hence this is contradict. From the assumption say that 2n is greatest. We found out 2n plus 2 is the greatest. Then this is contradict. And this is contradict the assumption that there contradict the assumption that the greatest integer is 2n. Therefore, there is no greatest even number. Hence, there is no greatest even number. Part B. If n square n cube is even, then n is even. So this is the statement. Is if n square is even, then n is even. So the assumption is there exists a number n such that there exists there exists a number such that if we see a if term, usually we are starting like this as well. There exists a number, there exists for all, there exists for all, then there exists, that is the negation. Start so if n there exists a number such that number n such that n cube is even, but n is odd. So n cube is even, then n is even. So we'll take n is odd, and we are getting instead of n cube, we'll find n cube and we will get odd numbers. So this is going to be contradict. So let's consider n equal 2m plus 1. M is element of real numbers. So this is how we write odd usually. Multiply by 2 and add 1. So then n cube is 2m plus 1 cube. So this is going to be, you can use a binomial. This is 2m cube, then 2m square 1 and 2m1 square and 1 cube. So this is 1 and 1. This is 3 and 3. 1, 2, 1. 1, 2, 1, 1, 3, 3, 1. Pascal triangle. So this is 8 cube plus 6m square plus 6m plus 1. Now, if I take 2 out, 4m cube plus 4m square plus, 3m square plus 3m plus 1. So, whatever this number, so 4m square plus 3m square plus 3m 3m can be odd or even, but 2 times 4m square plus 3m square plus 3m is even, definitely, if you multiply by I think this is 2 square 4, this is going to be 12. So this is 12 when you take 2 out, this is 6. So this is 6m and 3m. So whatever, but 2 is even. Then 2 times 4m square plus 6m square plus 3m plus 1 is odd. Hence, what is this one? This is n cube. N cube is odd. The assumption say n is odd, but and n cube is even. But we came to know now n cube is odd. N is odd, but n cube also odd instead of even. So now this is contradict. So we have to write this contradict the assumption. This contradict the assumption that n cube is even. Hence, if n cube is even, then n must be even. Before you start, just see that this is whether true or no. So let's say when n equal 2, what is the 2 cube? Whether even or odd? Yeah, it is even. Take any even number, 4. What is 4 cube? 64. So this is 8, even. 64, even. So it works. Part C, a statement. If PQ is even, then at least one of P and Q is even. If PQ is even, assume that there is a number, let's say 64. If we can break into two numbers, 8 times 8. So now this is P and this is Q. So we know at least one of this one. So we know P also even, Q is also even. So that is fine, at least one even. How about 15? We can break 3 times 5. So then this is going to be, so 15 is not even. We can't take this one. Any other one? 22. So 2 times 11. I can write in 2 factors. Then 2 is even, 11 is odd. But still fine, at least 1 is even. So this is the idea behind it. So we want to show that this is true. So then we are going to write the negation, some assumption. So if PQ is even, if PQ is even, then neither P nor Q is even. No one is even, P or Q. So then they has to be odd. So we'll consider now. Uh, let's take P equal odd. How do we write? 2m plus 1. M is the element of real number. So take any number from the number line, multiply by 2 and add 1. It will become a. So this is the standard way of writing a odd number. So let take Q equal 2n plus 1. N also such number in the number line. So then we'll find PQ. 2m plus 1 times 2n plus 1. When you multiply 2m times 2n plus 1 and plus 1 times 2n plus 1. So 4mn plus 2m plus 2n plus 1. I use this chance to explain something. So now I can do this one by looking at this one. 2m times 2, this is 4m n, then 2m, 2 times m, 2m, then 1 times 2n plus 1. So when you are in a stress situation, we should know you shouldn't do this kind of thing, because there could be an error. There is a chance of doing errors in a pressurized situation, for example in exam. So best way, 2m, use a technique, plus 1 times 2n plus 1. So this is very short. 4mn plus 2m plus 2n plus 1. So then I can factorize 2. This is 2mn plus m plus n plus 1. So then the argument is 2mn plus m plus n, can be odd or even, can be odd or even, but 2 times 2mn plus m plus n is even, and 2 times 2mn plus m plus n plus 1 is odd. Now, so this is contradict now. So we say that in the assumption it say that PQ is odd, then PQ has to be even. But we prove now PQ is odd, and P and Q is odd, and PQ also odd. This is contradict the assumption. This contradicts the assumption that PQ is even. Therefore, if PQ is even, then at least one of P and Q is even. Part D, we want to show that if P plus Q is odd, then at least one of P and Q is odd. At least one of P and Q is odd. So if we consider odd number 5, if I write as a factor 2 plus 3, so this is P plus Q form. So at least 1 is odd, 3 is odd, so at least 1 is odd. Or 9, 7 plus 2, 1 plus 8. At least 1 is odd of these combinations. We'll write the negation now. Assumption, if P plus Q is odd, then neither P nor Q is odd. So same as earlier, so we have to take P and Q. So neither P nor Q is odd, then only possibility is even. So let P equal to M. M is element of R, and Q is 2N. N is element of R. Then P plus Q is 2M plus 2N equal 2 times M plus N. We know that M plus N also element of R. So now we can tell that M plus N can be odd or even, but 2 times M plus N is even. So our argument is now, if this is even, if P and Q even, P plus Q is odd. But we take P and Q even, and we end up with P plus Q also even. So this is now contradict. So this contradict the assumption that P plus Q is odd. Hence, if P plus Q is odd, then at least one of P and Q is odd. Statement, if A, question number 5, if AB is an irrational number, then at least one of A and B is an irrational number. So AB is an irrational number. If you take 2 square root 2 or 3 square root 2, so we know that this is a irrational number. Then we know that this is 3 and square root 2 multiplied by together. So we know that one is irrational. This is true. Now we need to show that, we need to prove that. So then assumption is, if AB is an irrational number, then neither A nor B is an irrational number. So if AB is an irrational number, neither A nor B is irrational. It means A and B is rational. So we know that if a number is rational, then we can write as a fraction. So M is element of R and N is element of R. If B is a rational number, then B we can write P divided by Q. P also a element of real number, Q also element of real number. Now let's discuss what is AB. AB is MP over NQ. So MP is an element of R, NQ is an element of R. Sorry, I have to do a small change. So this is an integer, is it? Integer. This is also integer. I think so. I need to write a correction. If I use in 4, question number 4a, real numbers are, so it has to be changed and it has to be integer, because there's a question A, there is a greatest even integer. There is a greatest even integer. So we take 2n, then n is, rather than is a real number, we have to write n is a element of z plus positive integer. We'll back to the sum now. So AB is MP divided by NQ. So MP, we know that M is an integer, P is an integer, 2 is an integer, 3 is an integer. When you multiply, also it is an integer. As same as NQ also an integer. So then they are two integers. So this is in P divided by Q form or as a fraction. MP is integer. This is the same idea. NQ is an integer. An integer. Same idea you will give when you write like this. Therefore, AB is a rational number. Now, A is irrational, B is irrational, and AB has to be AB rational, B A rational, B rational, but AB is irrational. So that is the assumption. But now A irrational, B rational, but AB also A rational, B rational, but AB also rational. Now this is contradict. This is contradict the assumption that is irrational. Hence, if AB is an irrational number, then at least one of A and B is an irrational. Question number 5 part B statement. Prove that A plus B is an irrational number, then at least one of A and B is an irrational number. If you take that as 2 plus square root 3, this is clearly irrational because 2 is just 2 and square root 3 going to be 1 plus, so infinite number of numbers. When you add 3 dot 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 dot, so it is going to be a irrational number. Now we need to prove this one. So our assumption is if a plus b is an irrational number, then neither a nor b is irrational. It means if a and b rational, a plus b is irrational. So that is the idea behind this one. Now, as usual, we'll take that a equal m over n, m our element of z, and n element of z, and then b p over q, p element of z, and q element of z. Then we'll add those two together. A plus b equal m over n plus p over q, which is mq plus pn plus nq. So, so mq. So combination of those two. So m element of z, q is hence mq element of z, and same as pn element of z, and then nq also element of z, and also mq. Actually we can write hence mq plus pn is element of z. The other one is nq is element of z. Hence or we can write one more step, mq plus pn equal r element of z, another one. So we can write now a plus b is r over nq. So I will make one r equal t element of z, r equal t. So then it is clear. Now this is the fractions. Hence a plus b is rational. Now it is contradict, because if a is rational, b is rational, a rational, b rational, then a plus b irrational. That's the assumption. But now a rational, b rational, and also a plus b also rational. Now this is contradicts. Now this contradicts the, hence this contradicts the assumption that a plus b is irrational. Hence we have to write p plus mppn equal r. Now conclusion is hence if a plus b is irrational, then at least one of a and b is irrational. If a plus b is. The idea behind this one, part C, if a plus b is a rational number, then at least one of a and b is rational number. We work with the other opposite one. If a plus b is an irrational number, then at least one of a and b is an irrational. Yeah, it's right. But this is not right. So we need to give a counter example. So 3 is rational. We can write 3 equal 3 over 1. So we can write two factors. One is let's say a 3 minus square root 2 and b is square root 2. So then a and b, then at least one of a and b is rational. Now here you can see this is not rational and this is not rational. So both are not rational. But still a plus b make rational. So the example is infinite number of example 3 minus square root 2 and b equal to square root 2. If I write this one, a plus b is rational, but a is irrational and b is irrational. Question number 6. The statement is there exists no integer a and b for which 21a plus 14b equal 1. So the assumption is there exist no integer exists integers a and b such that 21a plus 14b equal 1. Now we need to give the proof. The idea is we know that integer plus integer is the integer. Now from here integer plus this is the integer, yeah, it matches this one. So we'll divide by 3. So this is going to be 7. 3a plus 2b equal 1 over 7. If a is an integer, then 3a is an integer. If b is an integer, then 2b is an integer. Integer plus integer or has to be integer, but which is not now. Then only possibility is the a and b cannot go integers. This is the argument we are going to give. So I'll take this 1. 1 divided by 7. So this is going to be 3a plus 14b equal 1 over 7. Right? So a is the element of integer, hence 3a is the element of integer. B is the element of integer, hence 3b, sorry, this is going to be divided by 7. 2b is the element of integer, hence 3a plus 2b should be an integer. The reason is sum of two integers always an integer. But 1 over 7 is not an integer. Hence, this contradicts assumption that there exists integer a and b such that 21a plus 14b equal 1. Hence, there exists no integers a and b for which 21a plus 14b equal 1. Question number 7. The statement is if n square is a multiple of 3, then n is a multiple of 3. If, okay, we'll take 9 square. Yeah, 9 square, which is 81. So 81 or 9 square is a multiple of 3, definitely, because this is 9. 9 times 9. Then this 9 also multiple of 3. N mean 9. So n square, and this is the n. N square and n. So now here 9. So 9 square also multiple of 3, because that is 9 times 9. Yeah, definitely. And this is 9, just multiple of 3. So which is true. So now the assumption. So if n square is a multiple of 3, but n is not a multiple of 3, not a multiple of 3. So then whole number line 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This whole number line we are dividing into 3. When we divide by a number 3, right, if it is answer is remainder is 0, then it is divisible by 3. Then remainder is 1, and then remainder is divided by 3. Answer plus remainder is 2. So remainder is 3, then it is going to be the this one. So if you take 1 divided by 3, we can't divide, so remainder is 1. 1 is here. 2 divided by 3, we can't divide, so remainder is 2. And then 3 divided by 3 is 1, and remainder is 0. 3 is here. 4 divided by 3 is remainder 1, so 4 is here. Then 5 divided by 3, 1, remainder 2, so 5 is here. And then 6 divided by 3, 2, remainder 0, then 6 is here. Then 7, 1, 2, 3, so 7 divided by 3, 2, and remainder 1, 7 is here. And 8 divided by 3 is 2, and remainder 2, so 8 is here. Then 9, so 9 divided by 3, remainder is 9 divided by 3 is 3, and remainder is 0. 9 is here. Now you can see that likewise I can continue up to my life finish then I can categorize whole number into a 3. So one is divisible by 3, another one is divisible by 3 and remainder 1, and divisible by 3 is remainder 2. So we can write any number divisible by 3, let's say n. So n equal 3k. K also number in any number when you take number line multiply by 3, yes, is divisible by 3. Then n 3k plus 1 mean, so remainder 1. This one n 3k plus 2 mean this is remainder 2. So all number line categorized into 3, divisible by 3, then divisible by 3 and remainder 1, and divisible by 3 and remainder 2. Now I want to pick up n is not a multiple of 3. N is not a multiple of 3. Then what are the possibilities? Then n can be either 3k plus 1 or 3k plus 2. So those are the possibilities exist. Just for your knowledge, assume that if something divided by 4, then n equal 4k. Other one is when you divide by remainder 1, n equal 4k plus 1. Another one divide by 2, n equal 4k plus 2. Other one divide by 4, 3, n equal 4k plus 3. Do you think that n divide by 3 plus 4? No. Then it will become to here. So likewise. 1 less, if this is 4, 1 less than the remainder always. If this is 2, 3, then the maximum remainder is 2. So now I need to pick up uh, n is not a multiple of 3. N is not the multiple of 3. Hence, there are two options. That is n equal to 3k plus 1 and n equal 3k plus 2. K is an element of z integer. Right? Case 1. When n equal 3k plus 1. So we'll find n square. N square is 3k plus 1 square again. So this is going to be 9k square plus 6k plus 1. Then this is when I factorize. This is going to be k square 3k square plus 2k. Then plus 1. Now we can clearly say that this is not a multiple of 3. So it is in this form. So this is not a multiple of 3. But according to this one, if n is not a multiple of 3, n square is a multiple of 3. But here now n is a multiple of not multiple of 3 and n square also not a multiple of 3. So this is contradict this assumption. Case 2. When n equal 3k plus 2, n square equal 3k plus 2 square, that is 9k square 12k plus 4. So when I factorize this one with 9k square 12k plus 4, I will break plus 3 and 1. Then I can take 3 out. 3k square 4k plus 1 times plus 1. Now this is not a multiple of 3. Now this is again contradicts. Hence this is contradict. If n square is a multiple of 3, but n is not a but n is not a multiple of 3. Hence, we'll write the answer. Hence, if n square is a multiple of 3, then n is a multiple of 3. Uh, Part B statement is square root 3 as an irrational. The same way we did square root 3 is an irrational. It's the same thing. Assumption. The square root 3 is a rational number. If square root 3 is a rational number, then we can write as a fraction. A in integer and B is an integer, and they are in their lowest factor. So assume fractions are in simplest term. It means no common factors between A and B. Now we'll take this one. We can write A equal square root 3B. Then I square this one. A square equal 3B square. This implies that A square is multiple of 3. Hence, A is a multiple of 3. We prove the part A. Then now if A is a multiple of 3, then I can write A as 3t. T is an element of Z. This is normal. If it is a multiple of 3, I can write. Now I'll substitute here. I put 1 from 1. I'll take this is 2 and 2. 3t square equal 3b square, which is 9t square equal 3b square. Then this is 3t square equal b square. Since b square equal 3t square, b square is a multiple of 3. Hence, from part A, b is a multiple of 3. Then if A and B both multiple of 3, this contradicts the statement that there are no common factors between A and B. And the last one, hence, square root 3 is an irrational number. Question number 8, we want to show that there are no integer solution to the equation to this equation. So assumption is there there is an integer solution to the equation. So our argument is we write minus x minus y, x plus y equal to. So then to become 2, we have few options. 1 times 2 is 2. 2 times 1 is 2. Minus 2 times minus 1 also 2. Minus 1 times minus 2 also 2. Right? So we will discuss what will happen in. So here we are discussing what will happen to here. So we'll take x minus y first equal 1. Then x plus y equal 2. Then when you solve this one, 2x equal, when you add those two together, and when you find, you will get x equal 3 over 2 and y equal minus half. So this is not an integer, this is not an integer, but our assumption is there is an integer solution, but they are not. So when you work out to this one also same, they are not. So we have 4 cases to discuss. X square minus y square equal x minus y, x plus y equal to. Hence, possible pairs are 1, 2, 2, 1, minus 1, minus 2, minus 2, minus 1. So, case 1, 1 and 2. So then, we'll write x minus y equal 1 and x plus y equal 2. Then this will give x equal 3 over 2 and y equal half. They are not integer solutions. Case 2, 2, 1. So x minus 1 equal to x plus y equal 1. Then x equal 3 over 2, y equal minus half. So they are not integer solutions. Case 3, minus 1, minus 2. X minus 1 equal minus 1, x plus equal minus 2. So this is going to be x equal minus 3 over 8, y equal minus half. So they are not integer solutions. And case 4, minus 2, minus 1. So x minus y equal minus 2, x plus 1 equal minus 1. So this is x equal minus 3 over 2, y equal half. So they are not integer solutions. So because of anything not integer solutions, but assumption, according to the assumption, this is an integer solution. So hence this contradicts the statement that there is an integer solution to x square minus y square equal to. Hence the conclusion. There are no integer solutions to the equation to the 4x square minus 5y equal to. And question number 9 statement. This is, we want to show that this is irrational. So assumption is this is rational. 2 1/3 is a rational number. If this is rational, we can write as a fraction. A 1/3 equal, 2 1/3 equal A over B, A our element of Z and B element of Z, and then we'll find the cube of this one. Okay, first of all, A equal to 1/3 B, then A cube equal to B third. So this will tell that, okay, we have one more assumption we miss to write here. It's an irrational number. Fraction is in the simple term. That means there is no common factors between A and B. And so now A cube is 2B cube here. That means A cube is even. This will imply that A cube is even. This implies that A is even. Then we can write that A equal 2 times M. M is the element of Z. I'll take this is 1 and this is 2. Now from 1 and 2, I'll substitute this one. Instead of A equal to Q cube, 2B cube. So this is going to be 4 8m cube equal to B cube. So this is divided by 4m cube equal B cube. So then this will imply B cube is the even number. This will imply B is even. If A and B are both even, then they will have a common factor of 2. There is no common factor, but now we come across have a common factor of 2, which is contradict. So this contradicts the statement that A and B have no common factors. Hence, we can conclude that the original hence 2 1/3 is a rational number, irrational number. Question number 10, when you read, you can see that the identify the error in the student's scope. So you will see that the number a minus b over b could be negative, and the other one is so he took least positive number is n, uh, and it is rational, positive rational number. So we can write a minus b. So then so he took n minus 1, that is a minus b, a over b minus 1, this is a minus b over b. So this is the issue. It could be negative because assume this is half. So a equal 1 and b equal 2. Then 1 minus 2 over 2. So this is going to be could be. So this is negative. So this is the issue. So example is n equal half or 1/3. So we want to show that there is no least positive rational number. So assumption is there is there is a least positive rational number, that is n, and then we'll take let n equal a over b, a element of z and b element of z, and so let's consider m a equal to b. So b is element of z, and hence 2b is element of z. So hence m is rational, but m is less than n. Hence this contradicts the statement that there is the least positive rational number. Hence, there is no least positive rational numbers number.